Hello, this lecture is about the last component of the Chute spillway design, that is the energy dissipation part. So, this is the last component, the energy dissipation. So, first we went through the Voge spillway, then the design principle of part 1, part 2, the last component is energy dissipation. So, what is the energy dissipation of below the spillway? Since water is flowing over the spillway, it requires lot of kinetic energy by the time it reaches near the toe of the spillway. That is, since the water is flowing from the top, so conversion of potential energy is into the kinetic energy. If the arrangements are not made to dissipate this huge kinetic energy of water, and if the velocity of water is not controlled, large scale scour or the erosion occur at the place at the downstream of the dam. So, arrangements is to be provided for energy dissipation, which is widely known as energy dissipators. In general, the kinetic energy of this supercritical flow can be dissipated in two ways. So, by converting the supercritical flow into subcritical flow by hydraulic jump, or by directing the flow of water into air and then making it fall away from the toe of structure. So, these are the two ways in which we can dissipate the energy. So, hydraulic jump formation. So, hydraulic jump can form in a horizontal rectangular channel when the following relation is satisfied between pre-jump and the post-jump depth. So, pre-jump is y 1 and the post-jump depth is y 2. So, all of you know that hydraulic jump can be created and then we can get the conjugate depth equation. So, this is the basic form of equation to be used for y 2 and y 1. So, for a given discharge intensity over the spillway and at a depth of y 1, so this is the first conjugate depth y 1 is equal to q by V 1. So, this is the discharge, this is the total energy line, this is H L the gradient, and H 1 the discharge is it is a y 1 is the ratio of the critical discharge divided by V 1, and V 1 is determined by the drop V 1 and equal to root under 2 G H. So, the entire equation comes out to be q upon 2 G H 1, where H 1 is the height and total energy line height of the total energy line from the dam bottom to this point. For a given discharge intensity and given height of the spillway, generally y 1 and y 2 are fixed. Availability of depth equal to y 2 in the channel on the downstream depends on the tailwater level, which depends on the hydraulic dimension and the slope of the river channel. If a graph is plotted between discharge and tailwater depth, a curve is obtained. This curve is called a tailwater curve. The graph between discharge, critical discharge and tailwater depth. If a curve is drawn, this is called tailwater curve. And if a graph is plotted in the curve is plotted in the same graph between q and conjugate depth y 2, the curve is known as jump water height curve. So, this is called TWC and this is called JHC or the y 2 curve. So, these are two different curves which is related to hydraulic jump formation. So, there are 5 possibilities in this case. So, the TWC or the tailwater curve when coincide with y 2 curve or the JHC curve. So, this looks as on the same point. So, this one is coinciding with this, where TWC is coinciding with JHC. This is depth and this is the critical discharge. And the second possibility is when TWC is lying above the Y2 curve. So, this is TWC curve, this is Y2 curve. And the third possibility can be if TWC is lying below the Y2 curve at all discharges. So, first one is TWC is above this, and the second one is just reverse the situation. There is a fourth condition when the TWC is lying above the Y2 curve at a smaller discharge and lying below the Y2 curve at a large discharge. The condition where both are intersecting, Y2 curve is below and TWC curve is the next stage, it is above. And the fifth condition is just reverse of this situation, where TWC curve lying below Y2 curve at smaller discharge and lying above the Y2 curve at a large discharge. So, these are the 5 different possibility that a hydraulic jump can generate a huge amount of energy. So, how to dissipate this energy? So, we will first go for case 1, when both the graphs are coinciding, when TWC coincide with Y2 curve at all discharges. This is the most ideal condition for the jump formation. The hydraulic jump will form at the toe of the spillway at all discharges. And in such case, a simple concrete apron of length 5 times Y2 minus Y1 is generally sufficient to provide protection in the region of hydraulic jump. So, this concrete length is, if you provide a concrete length, this is the simple solution for this. So, this is the condition. Here there is a formation of hydraulic jump and you provide a simple horizontal apron in this case, and this is the seal, end seal here. Now, coming to case 2, when the TWC is lying above the Y2 curve at all discharges. When Y2 is always below the tailwater, the jump forming at the toe will be drowned out by the tailwater. And in this case, what happens? A little energy will be dissipated. This problem can be solved by 2 or 3 ways. So, first we will go by constructing sloping apron above the river bed. This we will going to show in the next slide. So, jump will form on the sloping apron where depth is equal to Y2. Second, slope of the apron is made in such a way that the proper condition for a jump will occur somewhere on the apron at all discharges. So, this is a sloping apron is provided above the bed. So, like this, and this is the end seal, and this is the hydraulic jump. This is the apron is going like this, and this slope. Now, the second way to solve this, and we are continuing the same case when TWC is lying above the Y2 at all discharges, the case 2. Second solution is to provide a roller bucket type energy dissipator. Roller, which is formed downstream of the bucket, tends to move the scored bed material towards the dam, thus preventing the serious score at the toe of the dam. Sometimes the scored material may enter the bucket under the action of upstream roller and may cause severe abrasion. So, what we can do in that case? A detented bucket lip may therefore have to be provided so as to permit removal of material caught inside the bucket. So, in the next slide I am going to show the structure. So, like this, a bucket kind of arrangement is to be provided, and this is sloping apron above the bed where there is a formation of whirlpool and there is a bucket kind of arrangement here. Now, when the TWC is lying below Y2 curve at all discharges. So, here this is the case 3. So, by providing a ski jump bucket energy dissipator, if tail water level is very low. So, we provide a ski jump kind of bucket here. The second way to solve this is by providing a sloping apron below the river bed. So, the same case 3 is continuing. that is when TWC is lying below the Y2 curve at all discharges. So, a sloping apron is provided below the river bed here. Now, the third way to solve this, construction of a subsidiary dam below the main dam. A subsidiary dam is to be constructed and that can take care of this energy dissipation problem. So, subsidiary dam is here. Now, we are going to see the case 4, when the TWC curve as the Y2 curve both are coinciding and the TWC is lying above the Y2 curve at small discharges and lying below the Y2 curve at all large discharges. So, this problem can be solved by providing a sloping apron partly above and partly below the ground level. So, this is my case 4 and this is a combination of case 1 and case 2. So, here we provide a sloping apron partly above and partly below the ground level. So, this way we can solve this kind of energy dissipation problem. And now the last case. The last case is when this also the case when TWC and Y2 curve both are intersecting, but the case is just opposite of case 4. That is, a TWC is lying below the Y2 curve at smaller discharges and lying above the Y2 curve at large discharges. So, here the arrangement will be same, the same arrangement which was made in case D will serve the purpose. Only difference will be that at low discharges the jump will form on the apron below the bed and at high discharges the jump will form the apron above the bed. So, this is the case 5, just that is a reverse of case 4, and this is the jump here is forming above the bed, below the bed, and at high discharge the jump will form on the apron above the bed, the last case. So, these are the 5 ways we can solve the energy dissipation problem. Now, coming to energy dissipation below other type of spillway. So, if the spillway are some other type, how we can solve this energy dissipation problem? So, first, a chute or a shaft or a side channel spillway generally discharges at a point away from the dam. Hence, the protection is required only for the spillway, as the danger to the main dam is not here. So, in this case, a hydraulic stilling basin generally sufficient and may be provided at a discharge point of the spillway. So, hydraulic stilling basin is sufficient to solve this kind of problem. However, if there is a rocks are available, in that case a ski jump bucket may be provided, which is at a low cost. Okay. So, and stilling, now the design. Now, hydraulic jump formation depends considerably upon the Froude number of the incoming flow. So, the pre-jump depth and post-jump depth or the conjugate depth are given by this formula. So, this is a Froude number here, and the Froude number is a ratio between V1 upon root G Y1, these two depth. If the incoming Froude number F1 is higher, the greater energy dissipation can take place. So, here we given the range of Froude number and corresponding percentage of energy loss. So, from its Froude number range from 2.5 to 20. So, 2.5 if the Froude number is low in number, on 17% loss of energy happened. However, if it is 20, around 85% losses can happen. And now, coming to types of jump for different ranges and their Froude number. When F1 is less than 2.5, the jump is weak and the energy loss is low. So, no blocks or other devices are provided in this range. So, we are basically safe in this range. However, when F1 lies between 2.5 to 4.5, the jump is now troublesome and oscillating and which gives rise heavy waves on the surface. So, in that case wave suppressor may be needed in this range and the length of the jump may be taken as a difference between y 2 minus y 1 and 5 times of this difference. When F1 lies between 4.5 and 9, the jump is steady. The length of the jump is almost constant and equal to 6 of y 2. Hence, for large spillways where y 2 may be quite high, very long expensive stilling basins may be required. Some auxiliary devices may also be introduced for further stabilizing the flow and to reduce the length of the basin. When F1 is 9 and larger, it is a strong jump, but the jump is likely to be rough and choppy. Bucket type energy dissipator is preferred in this case and of this hydraulic jump type. Now, the kind of stilling basin. So, various kind of stilling basins have been generalized for use on different types of work and various agencies. So, design of this basin have been developed on the basis of long experience and model studies. So, these basins are not simple concrete apron, but generally provided with an auxiliary devices. This device can help in dissipating energy of flow by offering resistance to flow and may stabilize the flow in shorter length of the basin. So, in general, a stilling basin may be defined as a structure in which the energy dissipation action is confined. So, stilling basin is a kind of structure in which energy dissipation can be taken place. So, this kind of auxiliary devices are designed for energy dissipation. So, one of them is chute blocks. So, chute blocks are a kind of serrated device and provided at the entrance of the stilling basin. So, you can see this point here at the entrance of the stilling basin, these small chute blocks are provided. So, incoming jet of water is furrowed and partly lifted from the floor, producing a shorter length of the jump and which would be produced here, and they also help in stabilizing the flow and then they can improve the jump performance in presence of these small blocks. Now, the other way of is to provide seal and detented seals here. Seal or detented seal is generally provided at the end of the stilling basin. So, detented seal diffuses the residual portion of the high velocity jet reaching at the end of the basin. They help in dissipating residual energy and to reduce the length of the jump or the basin. So, these are the stilling basin here. The third way is to provide baffle piers. So, baffle piers are like this is the end seal and this is the chute blocks and now you have the baffle piers. So, they are the small blocks placed within the basin and across the basin floor. So, they help in breaking the flow and dissipate the energy impact mostly by the impact. So, these baffle piers, sometimes also called as friction blocks, are very useful for the small structure. However, for large structure these are not suitable. Now, another way is USBR stilling basin 2. So, this is the stilling basin 2 structure. This is recommended for use on the large structures such as dam, spillway and large canal structure. These are used when the incoming fraud number is more than 4.5. So, for large structure these are the basic device to be used. Now, the relation between basin length and the fraud number. So, if the fraud number is 4, so the length of the basin is to be kept as 3.6 times y 2. Then at a 2 interval, if it is 6, then 4 times y 2, 8, 4.2 times y 2, 10 or more 4.3 times y 2. an economy in the length of the basin of up to about 35%. So, 4.3 y 2 in place of 6 y 2 is thus obtained by these auxiliary devices. The floor of the basin should be set at such a level as to provide 5% more water depth than y 2. So, if you remember the design we we kept as 5% more of y 2 in the water depth in earlier slides. So, US Beer Stilling Basin 4, it is used for fraud number varying from 2.5 to 4.5, which is generally occurs in canal weirs, canal falls, diversion dam, etc. So, this basin is applicable only to rectangular cross section. Since oscillating waves are generated in this range of fraud number, they are tried to control at a source by providing large chute blocks. So, this is USBR Stilling Basin 4. Here, so this is the top surface of the 5° angle. So, length of the basin and still is optional, and the floor of the basin must be set in such a way that level provide 5 to 10% more water depth than its theoretical y 1 value. So, so the floor is to be kept in such a way, so it can provide 5 to 10% more water depth, and the length of the basin is generally kept as the 5 times the difference between y 2 and y 1, the conjugate depth and the pre-jump depth. So, thank you.